So the simple linear regression, in the simple linear regression, we are having one input and one output. So like x and y. So x is the dependent variable and y will be the independent variable. Here the y is the output variable which we have to predict based on the value of the x. So in this example, let's consider x has height of a person and y has the weight of the person. So if 5 feet tall person has 60 kg of weight and 6 feet tall person has 70 kg of weight and 5.5 feet tall has 65 kg of weight. So this is linear regression and there is a linear relation between x and y. So when we plot it graphically, it will something look like x axis will be the input variable height and y axis will be the output variable weight, and these points are the values of the y predicted values or actual values. These are the actual values, and in the linear regression model we have to find the best fit line. Our goal is to detect the best fit line such that the error is minimal. What is the error here? So error is the distance between the best fit line and the actual value of y. The actual value and the distance between the best fit line, the predicted value, is the error, and our goal is to find the best fit line in such a way that the error will be minimum. The equation of the linear regression is h theta of x is equal to theta naught plus theta 1 of x, where theta naught is the intercept. That means intercept, this point. This point is the intercept, and theta 1 will be the slope or the coefficient of the best fit line, and h naught of x is the y hat, that is the predicted value by the model. So error is actual minus predicted, that is y minus y hat. Suppose for example for 5 feet tall the weight is the actual value is 60 kg, but our machine has predicted it has 57 kg. Then the y minus y hat will be the 3 kg. Sorry, this is wrong, not 5. It will be the 3 kg. 60 minus 57, that is the 3. The error is 3. So our goal is to find the best fit line where the error, summation of all the errors means this is the error 1 and this will be the error 2 and this is the error 3. So this is the error 4 for every point which the machine has predicted. It will calculate the actual minus predicted, and we will have to find the error. Summation of the error should be minimum. To find the minimal error, we use the cost function. So in the cost function is j of theta naught theta 1 is equal to 1 by 2n. Summation of I is equal to 1 to n h theta of x of I minus y of I whole square, that is y hat minus y, actual minus predicted whole square, and n is number of data points. Suppose we have 100 records, then it is 100. Suppose we have 200 or 1000 records, so n is the number of data points. So this is our goal to minimize. So by using the cost function we have to find the minimum error, that is known as global minima. That is known as global minima. And how we have to find it? We have to find it by changing the theta naught and theta 1 value. By changing the theta value, we have to reach a point where the error should be minimum. For this we are using the gradient descent curve. This concept is known as gradient descent curve. Suppose this is the slope or coefficient. Consider it as the coefficient of x theta, and this is the j of theta, our cost function. So we will start at some random point at this theta value, where we will start from lesser theta values to greater theta values. Suppose our theta value is 0.05 and j of theta is here. Okay, and we have to find the slope of this. Here at this point it will draw a point, it will draw the tangent line and find the slope. Based on the slope, the gradient descent curve will converge and shift to the next point, where and it will calculate the cost function again, and it will draw the tangent line and it will converge, and at this point it will draw the tangent line and it will converge. So this is the gradient descent curve. For this we have to apply the convergence algorithm. So what is convergence algorithm and how the gradient descent curve work mathematically, we can learn here. So convergence algorithm is used to optimize the change of theta value. It basically means repeat until convergence. The convergence algorithm is theta value. Theta j is equal to theta j minus alpha derivative of theta j with respect to j of theta. So what is the alpha value? Alpha is the learning rate at which the convergence should happen. So alpha value is standardly we use 0.02. So learning rate should be very less, so that the gradient descent curve will converge slowly. If we keep the alpha value more, the learning rate more, then the curve will be like this and this and this. So it will keep traversing from positive to negative, negative to positive, and we will never reach the global minima. So it is very important to keep the learning rate very less, like 0.02, 0.03. So our curve should converge slowly. See? And the derivative of j of theta with respect to theta j gives the slope of the tangent line. I said this is the tangent line. For point 1, this is the tangent line. Okay. For some theta value, for first theta value, for the point 1, the tangent, this is the tangent line, and derivative of j of theta j will be negative because the slope is negative here, and the negative value is multiplied with the negative value, it becomes positive. So minus into minus is positive. That means we have to increase the theta j value. If the slope of the tangent line is negative, we have to increase the theta j value. Same for the point 2. Again the slope is negative, so the theta j value will increase. Point 3, the slope is negative, the theta j value will increase. And point 4, the slope is negative, the theta j value will increase. But for point 5, the theta j value will increase because the slope is positive. When it is positive, the slope is positive, it will be multiplied by negative minus alpha, and it will becomes minus, and the theta j value will decrease. So when theta j value decreases, it again come back to 0.4. So it performs 0.6. Again the theta j, it indicates theta j should be decreased. This is not the right error. This is not the global minima. So it will keep decreasing. If your curve starts from this point, it will keep decreasing, and if your curve starts from this point, then the theta j value keeps increasing, and ultimately we will reach the global minima, which will be our minimum error for the best fit line, which is our minimum error for the best fit line, and that theta value will be used in our cost function. Okay, so that theta value will be used here in the cost function, and will get the best fit line. Same thing I have mentioned here. For point 1, 2, 3 and 4, slope is negative, tangent line slope is negative, then the equation will be theta j minus alpha of negative of x value. That means theta j plus alpha, which means the increase in theta j value. For point 5 and 6, that it will be positive, the slope is positive, which means decrease the theta j value. So this completes the simple linear regression model, where we have only one dependent variable and one independent variable. In the multiple regression, there is one independent variable, that is y, and multiple dependent variables are input variables. So x1, x2, x3 and x4 are the independent variables. and y is dependent variable, only one output variable. And the equation will be h theta of x is equal to theta naught plus theta 1 of x plus theta 2 of x2 plus theta 3 of x3. So x1, x2, x3 are the independent variables, and theta naught is the intercept, and theta 1 is the coefficient of x1, theta 2 is the coefficient of x2. For this multiple linear regression, gradient descent curve will something look like this. So it will be a like 3D or 4D based on the number of features you have, number of independent features you got. So how to measure the performance of the linear model? So the best way is the R squared. There are multiple ways like mean squared error, mean absolute error, R square, adjusted R square. I am going to explain you all of those. So the first is R squared method. What is the formula of R squared? 1 minus sum of square of residuals minus sum of square of total. So what is residual? Residual is nothing but y minus y hat, actual minus predicted. So these are the actual points, okay, and these red points are the predicted points. So distance between this, actual minus predicted, y minus y hat, y minus y hat. So this is the residual, summation of this 1 minus summation of sum of residuals and the total. What is total? So for the predicted values y hat, we will calculate the average of y, average of actual y, and we will draw a line here. So this is average of all the output variables. So actual value minus average of output variable y bar. So that is y minus y bar is the total. So the R square will be 1 minus summation of y1 minus y hat divided by summation of y minus y bar square. That means average of the output variable. If the R squared value is near to 1, suppose like 0.0, 0.8, 0.9, 0.95, then the model accuracy is good. Like if it is near to 1, the model accuracy is good. If it is far from 1, then model accuracy is not good. So adjusted R square. Suppose what is adjusted R square, and the question is why we need adjusted R square when we already have the R square. In the data sets, like real world data sets, there are some features which does not make any impact on the dependent variable, output variable y, but they are still in our data, which increases the accuracy because we are adding extra features or extra parameters, we can call input variables. They will increase your accuracy of the model, but actually there doesn't make any impact on the output variable. So let's consider example here. Suppose we have a data set of only two features. One is flight ticket. Okay, so here the input variable is, the independent variable is distance, and the output variable is price of the flight ticket. So if distance is more, then the flight ticket price will also be more. So this is linearly positive linear relationship between the x1 and y, x and y. So if distance increases, the price also increases. So this has major effect on your flight ticket price. So this is a very good input variable. And our R square value for this is 0.75. After building a model, consider we got an accuracy, model accuracy of 0.75. And next variable, we'll add one more variable to our data set, that is class. The class can be your flight ticket, economy class, first class, or business class. So depend on the luxury of the ticket you book, depend on the class of the ticket you book, the price of the ticket will definitely increase. So this has a linear relation For economy it is less, for first class it is bit higher than economy, and for business class the flight ticket price is very high. So this is completely a linear relationship between class and your output variable price. Then the model accuracy, when you add two very good independent variables, input variables, distance and class, the model accuracy will increase to 0.8, that is 80% the model is accurate. Suppose now we add one more variable, that is gender. So you might be a male, the passenger might be a male or female. How does this affect the flight ticket price? So it doesn't affect the flight ticket price, right? He can be a male, the passenger can be a male, or passenger can be a female. That doesn't matter. But still, when you add the input variable gender, it does not have any correlation with the output variable. The model accuracy is still increasing, that is 0.85. Why? So this is a wrong addition of feature. That's why we need the adjusted R square, which will penalize the feature that are not correlated with the output variable. That's what I mentioned. By addition of unrelated feature, the model accuracy is increasing. This is the major drawback of R square. Adjusted R square penalizes with respect to every feature that are not correlated with the output variable y. So what is the formula for adjusted R square? 1 minus R square, n is number of data points, minus 1, n minus p. See, here we are having number of independent features. Since the p is in denominator, the number of independent features. So if R square value is considered 0.9, that is 90%. So when for number of input variables are 2 and the R square value is 0.9. So here the parameter will be 2. And the number of parameters increases to 3, then this value also increases. The parameter value increases. So R square in general, adjusted R square is, the value you get for adjusted R square is less than the R square. So this way it penalizes the input features which are not correlated with the output. So once the model is built, we have to check whether the model is overfitting or underfitting. So what we do is, first thing, when we build the model, we split the data. We split the data into two major parts. One is training data set and test data set. Test data set is for testing the model. Once it is untouched, the machine has never seen this data. So when it is used to predict the new values and check the model accuracy. But training data is used to train the model. In the training data, we will split training data again into two subcategories. One is train data for training the model. Other is validation data for hyperparameter tuning the model. In some cases, what happens is, generalized model. Suppose the model is good, the training accuracy is also good, and test accuracy will also be good. That means low bias and low variance. The model is generalized, the model is good. In the overfitting model, what happens? The training accuracy is high. Suppose the training accuracy is 90%. But when you check with the test data, when you give machine the test data, the test accuracy is low. For the unseen data, the predictions are wrong, the error is high. So the test accuracy is low. That means it is overfitting model. It is low bias and high variance. And in the underfitting model, both the training accuracy is also low and test accuracy is also low. That means high bias and high variance. So we have to check this, whether the model is overfitting or underfitting, by splitting the data set into two categories, training and test data set. This completes your theoretical part of linear regression. Next, I will give a demonstration of practical implementation of linear regression model. How to build a linear regression model? Our main focus will be on building the linear regression model. For building a linear regression model, I have used the car purchase amount prediction dataset. The dataset I have downloaded it from the Kaggle. So it is basically to build an predictive models to understand customer. For the practical demonstration of the linear regression, I have used the car purchase amount prediction data. So the data and the model is built to understand the customer purchasing power, improve marketing strategies, personalize offer, and optimize sales decisions. So first we have to import the necessary libraries like pandas, matplotlib for visualization, seaborn, etc. So load the data. Df is equal to pd.read_csv. Using the pandas function read csv, we are loading the data, and this is the head, like means the first 5 rows of the data. Df.head gives you, if you mention the number here 5, it will give the first 5 rows of the data. So the data contains customer name, customer email id, country. The country usually it is the USA data, so all the country value is USA. And the gender 0 is for female and 1 is for male. And the age in years: 42-year-old, 41-year-old, 58-year-old, 57-year-old. And the annual salary of the customer, that is $62,000, $66,000. And total credit card debit he has, like the customer Martina has the credit card debit of $11,000. And the net worth, so the total wealth they have, the total wealth they own, that is 23,000, which is greater than the annual salary. And the car purchased amount they spend, so the power of the customer to spend on a vehicle or to buy a car is $35,000, $45,000. So these are in US dollars. So this is the data description which I mentioned, it is the same here. And let's check how the data is. df.info, it gives you the detailed description of the data, like it has 500 entries. You can see here 500 rows, that means you have 500 data points. And you have 9 columns, 0 to 8. You have the 9 columns: customer name, email, gender, annual salary, net worth, car purchase amount. And the data type of the column, so customer name, email, and country are the objects, the string types. Gender and age are the integer type, and annual salary, credit card, net worth, car purchase amount are float type. And one thing is, these are independent variables: customer name, age, gender, annual salary, and net worth. These are independent variables, these are x. And car purchase amount, y, this is dependent variable. So we have to build a linear regression model which will predict the car purchase amount. So for the descriptive statistics, we use df data frame data.describe function. It will give you the descriptive statistics of the numerical columns in a table format. Here the count is number of records, so every column has 500 of records. The mean, so gender mean, it doesn't matter, but the age mean is 46, and standard deviation is 7. What does this says? So you have to understand this. I will explain you. First let me explain the values. Count gives you the number of rows, mean gives you the median average value, standard deviation gives you the variance, minimum value the least value, and the maximum value is the maximum annual salary, like maximum age, it gives that. and 25%, 50%, 75%. What are these? These are quantiles. 25% first quartile, second quartile, and third quartile. These are used for identifying the outliers when you use the IQR method, interquartile range methods. So these are quantiles. Okay, so here I will focus on the descriptive statistics and try to explain you something. So mean age is 46. That means in our data set the customers are aged, mean average age of the customer is 46 and standard deviation is 7.9. that means 8 years. Consider 8 years. So the customers are varying between 46 plus 8 and 46 minus 8, plus or minus 8 years. So most of the customers are in this range. So that what this specifies. And annual salary, it is C. The mean is 62,000 and the standard deviation is 11,000. So most of the customers, like majority of the customers, salary varies between 11,000 plus or minus. Same for credit card, net worth, and car purchase amount. So let's analyze this. I have made the analysis and written the interpretation for you. We'll focus on the age first. Gender is either it is male or female, and a mean is 50%, 0.5. that means 50% of males and 50% of female. So equal distribution, like kind of male and female, they have gender distribution is equal in our data. So let's focus on the age. The mean is 46, that means 46 years of age, and standard deviation is 8 years, indicating most customers are within approximately 8 years of the average age. And the youngest is 21, that is minimum, and oldest is 70. And the 25th percentile, 75th percentile are 41 and 52 years. Annual salary, see, it is very close to mean. Median salary, standard deviation, lowest salary and the highest salary. Lowest salary is 28,000 and highest salary is $100,000. That is like there is a vast difference. Credit card debt, so it also same. See, approximately 3,500 is the variation from the customer debt. The mean debt is 9,000, so it is either 12,000 or 6,000. So most of the customers are between in this range, and there is no skewed. We will go for the skew distribution in the visual. I will give you the visualization of that. So for all the descriptive statistics, I have written the analysis, I have written the interpretation. So next thing is checking the missing values. Does our data has any null values, nan values, unknown values? So for that the best method is df dot isNull.sum. isNull.sum gives you the sum of null values. So none of my columns has the null values, all are 0. I have used a kind of clean data set because our focus is on building the model, not the feature engineering or data cleaning. When we check the duplicate records, that is df.duplicated.sum, it is also 0. So there are no duplicated records. Let's perform the exploratory data analysis, univariate analysis. So matplotlib and seaborn, plotly and seaborn, SNS. I have imported here, import seaborn as SNS. So I am using seaborn, and to plot the graphs I have used matplotlib.pyplot as PLT. So I am using these libraries to plot the graphs. So the univariate analysis, let's see the distribution of age. So df of age and KD is equal to true. This KD is equal to true gives you the line on the graph. Can you see the dark red line here? This is the KD. If you don't specify this parameter, you will just get the histogram. There will be no line. So it is good practice to use the KD because you get a good graphical presentation. So distribution of age looks symmetric. There is no left or right skewness. It looks symmetric distribution, normal distribution. Same for the distribution of annual salary. it is a normal distribution. And again, the distribution of credit card debt, it is a normal distribution. The code is same, I have just changed the column names in my data. The net worth distribution, it is kind of bimodal but not too bimodal, so we can consider this as normal distribution. Car purchase amount is also very symmetric. It is very good normal distribution. It is like a perfect normal distribution, the output variable. Let's see the gender distribution. For this I have made the bar plot or the count plot, you can say the count plot. It looks same, like both male and female are like same numbers. So to check, I have used dot value counts. So in my 500 records, I have 253 males and 247 females, like approximately same, like 250. So approximately they are same, they are equal distributed, male and female, both the genders. So for the bivariate analysis, I will do the bivariate analysis with the dependent variable y, that is car purchase amount, with each of the independent variables x values, but I have not considered the customer name, customer email and country. These are categorical variables, these are numerical variables, and this does not make much impact on the purchase amount, that I will show you in the later part. So that's why I have used only the numerical variables and try to get the relationship between the output variable and input variable. When we plot it, I plot the scatter plot by age and car purchase amount, you can see there is a linear relationship. As the age increases, the purchasing power, the purchasing amount of a person, the purchasing amount of a customer also increases. So this is a very linear relation. As the savings increases, because net worth increases as the person grows old, we can say that customer purchase amount increases. Same with the annual salary and car purchase amount. Again, there is a very strong positive linear relationship. I can see that as the salary increases, the car purchase amount increases. So it is very linear, very dependent. We have a good relation between the annual salary and age. So net worth versus car purchase amount, it is linear but not a very strong, I can say, because the data points also scattered here. Even the net worth is less, there are still many customers who are buying the car. It is quite a linear but not a very strong linear relation. Credit card debt versus car purchase amount. See, I can't find much linear relation here. There is it is not very linear related because the data is randomly scattered, and the credit card here the data is more between the 7,500 to 1,500. The debt, the customers are more buying the cars here, car purchase amount. It doesn't not much linear relation. And gender, I don't think it is going to make any impact on car purchase, because both male and both female will buy the cars, both drive the cars. So I don't think. See here in the box plot, I have plotted box plot for this. So see, the median is same, the 25th percentile, the 75th percentile, the min value and max values are same. So gender does not make much impact. So let's find how much impact is making. What is the definite relation between the input variables and output variable y. So for that I have made a correlation matrix where I have taken the columns gender, age, annual salary, credit card, net worth, car purchase amount, and dot corsi df. Okay, select the numerical columns, and dot corr, this is the correlation. It gives you the correlation between the between the each variables, between each other, like the gender with age. gender with annual salary, credit card, net worth, car purchase amount. So this has very good. So let me explain you something. Yeah. So annual salary, okay. Annual salary has a good linear relationship, means positive. It is, see, this is negative, this is positive. So positive of 0.61, that is 61%, or 0.61 linear, positive linear relationship with the car purchase amount. So this is a good linear. This variable has a good impact on the output variable. And this dot core, this finding the correlation matrix, will also help you to identify the multicollinearity. What is multicollinearity? For the annual salary and see the net worth. Net worth and annual salary, it is not much correlated. 0.014. Okay. So if the linear relation between the independent variables like x variables is more, not only the with the y variable, between the x variable, like for x1 and x2, if they are highly correlated, what does it says? It is difficult to identify the individual effect of the variable. So it will be difficult for you to identify the individual effect of variable, and small change in data can make a large change in coefficient estimates. So multicollinearity, small change, if you make a small change in the data, if there is a small increase or decrease, if there is a multicollinearity between two independent variables x1 and x2, it will make a higher impact on your model, and you cannot identify the individual effect of each dependent variable. So in such cases, here it is, there is no multicollinearity, but in some cases you might find multicollinearity. So the best practice is to drop the either of the column. If two columns are there is a multicollinearity between two columns, so the best practice is to drop one of the features. For example, if our annual salary and net worth has the linear relation of 0.9, then let's us drop net worth or annual salary, anything is fine. Heat map gives this a very good visualization. See, the bluer side is, if it is blue side, then relationship is less, and if it towards the red side, then linear relation is high. So if you see two columns here, 0.63 age and car purchase amount, plus the annual salary 0.62, which car purchase, has a very good linear relation. And the net worth, it has 0.49, approximately 0.5. So this net worth, annual salary and age has very good linear relation when compared to other columns. So this is the heat map. Heat map gives you a very good graphical representation of the correlation between the input variables and between the input and output variable. So this is the code. It is a very easy code. See, SNS Seaborn, I have used Seaborn dot heat map, and what matrix I want? Correlation matrix, and not equal to true means I want the numbers here 0.07, 0.04, 0. I want the linear relation number, correlation number. It gives you the not value, and C map is equal to cool warm. So basically this is color. You can change to other colors, font color and line width. So these are like parameters, you can change this. Plot dot title, this is the title, correlation heat map, and plot dot show. So this is the heat map, and our interpretations of heat map are age, annual salary and net worth have a good linear relationship, positive linear relation with the car purchase amount. Another way is pair plot. You can also use the pair plot to identify, see, age and annual salary, positive linear relation with the car purchase amount. Net worth has a positive relation with the car purchase amount. So you can also use the pair plot to visually identify the linear relation, but I prefer the metrics I prefer the matrix and heat map. Heat map is very good. I always choose the heat map. So next comes the feature engineering. As I said, the customer name, email, and country. Country, see, this is the USA data, so it doesn't affect which country, and we have only one country. So I will drop the country. And email. What should car purchase amount do? Has to do with the customer email and customer name. We don't want these columns. These are unnecessary columns. So first step is I'm going to drop these columns. So columns to drop, I will make a list. So this is a list of columns: customer name, email, and country. So then I use df is equal to new equal to df dot drop columns equal to, and you can specify individual columns. What I have done is I have prepared a list of columns and specified the name of that list, columns to drop. So it will drop the new columns in the list and create a new data frame, df underscore new. Why I have done this is I don't want to change my original data which I have loaded here. df is equal to pd dot read csv. This is the my original data set. I don't want to make any changes here. I don't want to disturb this data. I want to keep it as it is. So I have created a new data frame, df underscore new, where it is df underscore new, in which I have dropped the columns customer name, email, and country from the original data frame. If you want to drop in the original data itself, in the original data frame which you have loaded itself, you just have to specify here access is equal to true, in access is equal to 1, in place equal to true. That is, you have to specify in place equal to true. If you specify in place equal to true, then the data will be dropped from the original data set. I don't want to disturb any original data set here. So I have created a new data frame, that is df underscore new. And if you display the records, you can see like we don't have name, email, and country here. We have only 5 input variables and 1 output variable, car purchase amount. For the outlier detection, what are the outliers? Outliers are like the extreme points. I will explain you. I have plotted the box plot all together here. It doesn't look good, so I have plotted a individual box plot here. So for the box plot of age, what data point can be an outlier? Suppose the age is between 20 to 70 in our data set. If there is a customer with the age of 100 or 150, or a customer with the age of 5 years or 10 years, then that is considered as outlier, extremely low or extremely high. Those are the outliers. So if you see here, the outliers, see this is the box plot, and min, this is the min, this is the 25th percentile, this line is the median, this is the 75th percentile, and this is the max. Okay, and see, this is not an outlier, it is 70, and this is 20, between 20 years, 20 to 25. These are not outliers. These points, if they are extreme, if you find any extreme points here, then these will be considered as outlier, and you have to remove this outlier by using the methods like IQR, interquartile range. But in this data set, I don't find any outliers for all the box plot. Look, it is not any extreme point, so I don't find any outliers here. So I will keep the data as it is. See here, these are not extreme points. These are just a point which is one point which is a bit more, like net worth is more, not extremely more. So no outliers. So next we have to do is the feature selection. So what is the feature selection? we have to identify the independent variables and dependent variables. So in our data we have gender, age, annual salary, credit card, net worth. These are our independent, and target is car purchase amount. We have to specify them in x. X will be the independent variables and y is the dependent variable. So what I use is my data frame df underscore new dot ilog. I have used the ilog function. This gives you all the rows. Take all the rows, and what columns I have to take. I have specified all the columns from 0 to all the columns, but not the -1 colon -1. -1 is in this order. If you go in this order, car purchase amount is -1, net worth is -2. If you specify -2 here, it will drop net worth and car purchase. If you specify -3 here, it will drop credit card, net worth and my car purchase amount. So for x, I have specified all the rows, and which columns, all the columns except -1. -1 is car purchase amount. And same thing I have done for y. In y, I have to select only car purchase amount. So all the rows dot ilog all the rows colon, and only one column, that is -1. From the reverse order, only one column you have to select. If you come in this order, it will be 0, 1, 2, 3, 4 and 5. This column index value will be 5. Yeah, I have went in the reverse order. It is easy, that's why -1. So x and y are specified. So x contains these columns and rows, and y contains only one column, that is car purchase amount. So once you have selected the features x and y, what columns will be the x and what columns will be the y. Now you have to split the data. For splitting, you have to use scikit-learn library. From scikit-learn dot model selection import train test split. What is splitting? I have to split 4 data. Now I have split 2 data sets. Okay, I have splitted my data frame into 2 data, that is x input and y output. Now again further I have to split x and y. How? I have shown you the diagram. See here. I have to split training dataset and test dataset. Here I am not doing the validation dataset because I am not doing any hyperparameter tuning. I can explain you in some upcoming projects. But here I am doing only the train dataset and test dataset. Okay. The train dataset again will be split into train and validation dataset when you do the hyperparameter tuning. So basically, after splitting x and y, after identifying x and y, you have to split x and y both in training and test dataset. So training will have x train and y train, and test will have x test and y test. So see, that's what I have done there. Train test split, x train, y train. Okay, x train, y train, x test, y test. Training data set, x train and y train, test data set, x test and y test. Then train test split, which is imported from scikit-learn dot model selection, x comma y. The test size is which data I have to split in train and test split, that is x and y, which I have selected in the feature selection, x and y. Split this into train test split, and test size is 0.2. I have specified here test size. What is test size? It can be 0.2 or 0.3. Standard practice is 0.2 or 0.25, that is 20%. That means test size 20% of the data used for testing and 80% of the data use it for training. That's what I am saying here. When you specify test size is equal to 0.2. And random state, you see the random state is 42. What is this random state? It ensures reproducibility. Means now your data has, train data has 80% and x test has 20%. So when you are training the model, okay, so see, if you check the shape, x train dot shape, x test dot shape, it is 400. 500's 80% is 400, and 500's 20% is 100. So we have split the data 80 into 80 is to 20. So random state is 42. So when it is training the model, it selects the 42 records. It will again split like 42, 42, 42. It will train the model 42, first 42, next 42, next random 42, next random 42. So it goes in an order to train the data. When testing also, it will, for the output variable also, it goes in the order there. So for every training, for every echo, we can say every echo, every part of training, it is going to use in a order of 42, 42, 42, 42, 42. So there will be a cyclic manner. That is the random state. It does not immediately put all the 400 records and train it. It will go by 42 when validation, because it has to validate also. Now feature scaling. So we have to standardize our data here. We have to make our data into a standard scalar. Why? See, I will show you the descriptive statistics. If you see here, the age minimum is 20 and maximum is 70, and annual salary minimum is 20,000 and maximum is 100,000. Credit card debt minimum is 100, maximum is 20,000. If you see this data, see, they are not on the same scale. For age it is less than 100, and for annual salary it is less than, it is between, it is in the thousand scale, between 20,000 to 100,000. And for the credit card, for net worth, you can see it is 1000, it is 100,000. So you have 1 2 3 4 5 6 zeros, 10 lakhs, 6 zeros. But for maximum of age is only 1 0, 70. So the scale is not right. So we have to bring all our features into a same scale where the measurement of those data will be in the same scale. We have to standardize our data. So the machine learns equally. So that machine learns easily. It can identify the features and its effects. We have to standardize our scaling. We have to standardize our data and put it on a common scale. See, it mentions here common scale. What is scaling? It will apply the z test, that is z is equal to x minus nu. I have specified here some x minus nu upon standard deviation, SD. X is data point and nu is mean divided by standard deviation, so that the mean of the feature column becomes 0 and standard becomes 1. That is our goal, to make the each feature mean is 0 and standard deviation has 1. Then it will be on a same scale. It will be on the same scale. For this we have to import libraries sklearn dot, from the sklearn we have to import standard scalar. Okay, the standard scalar. Next is xtrain. So we have to scale only the input variables. Xtrain scalar dot fit transform xtrain. And for x test we are using only transform. For train we are used the fit transform. For test we have used only transform. Why? This is to prevent the data leakage. I have mentioned it, the data leakage, to avoid the data leakage. What is the data leakage? What we are doing is we are fitting the values by applying the z score, x minus nu upon standard deviation, only on our training data set and fitting it on a scale. Okay, but we don't want our machine, the machine, to see the test data. this should be an unseen data. That's why we apply only transform. So it will transform based on this. What are the features of train? The same features will be applied for the X test. It will just transform. It does not do any fitting. It does not do any fitting. It does not apply the Z score. It just transforms. So this avoids the data leakage. Okay. This is very important. You can, if you apply both fit and transform for both X train and X test, then there is a data leakage. That means the machine has seen your testing data. So you have to keep the testing data unseen. You should not show your test data to the machine. So you have to just transform the test data, but for training data you have to fit and transform. So keep that in mind. It is a very important step. So we have to build a linear regression. Our data is ready now. We have selected our features, we have dropped the columns, we have selected our features, we have scaled our features. Now we have to build the model using our features. We have also splitted the data into train and test. So when building the model, I will use the again sklearn. Okay, from scikit-learn I will import linear regression model, and I will fit what I will fit into my model, linear regression model: training data, X train scaled. That is, after scaling, my X train has become X train scaled, and Y train, my car purchase amount, that is output variable. Our model is built now. It has built the model. It has trained our linear regression model. So let's see the intercept which I have mentioned here. Multiple multiple linear regression model equation h theta naught plus theta 1 x1. So let's see the intercept is theta naught, that is 43,946. so this is the intercept, and coefficients, that is theta 1, theta 2, theta 3, theta 4. The coefficients, these are the coefficients of our model. So this is the equation, right? Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, or theta naught, theta 1, theta 2. That's all. It doesn't make any difference. There are different formats of writing the equation. So beta naught is intercept. So beta naught value is the intercept, and coefficient value is beta 1, beta 2, beta 3. So if you see, our beta naught is this, and our complete equation, I have written the complete equation here based on the intercept and the coefficients we have got. What does it says? What does it says? So interpret this equation. What does it says? Intercept is this. Okay, let's keep this all as 0. Age, annual salary, credit card, network, everything is 0, and gender is this. So for every 1 unit change in gender, the car purchase amount will be affected by 21.43, 21.41. Okay, the car purchase amount. So this is a positive coefficient because it has positive relation. For example, the annual salary, I will explain you the annual salary. Okay, gender is 0, age is 0, we are not considering anything, just the annual salary. If 1 unit of annual salary increases, if there is a 1 unit increase in the annual salary, then car purchase amount will increase by 6,686, because this is positive correlation, so it increases. If it is negative correlation, the car purchase amount will decreases. For 1 unit change, it will be 6,000. Coefficient describes that. For 1 unit change, what will be the effect of the independent variable annual salary on the dependent variable car purchase amount for 1 unit change? This is the interpretation of the equation, I have also mentioned the interpretation, complete interpretation here. You can go through this. I have provided the GitHub link in the description. So you can open the notebook and go through the detailed interpretation which I have mentioned here about the equation which we have derived. Okay, the link will be in the description, my GitHub link. So you have we have built the model, we have got the intercept and coefficient, so we have got our model equation. Now let's make a prediction. Let's see what is our y hat. So y minus y hat, you remember y. So y, let's see, we have to find see y hat, actual error. See y hat, we will find our y hat by giving the test data. See x test, this is unseen data, right? By giving the unseen input variables, we are predicting, we are making the y hat, we are finding the y hat data. We have made the predictions and let's compare. So this is y test which we have got, which is our training data, test data, actual y test values which we have got in the train test split. This is y test, okay, which is the split data, unseen data. I have given the input variables and got the output variable, predicted data, which the machine has predicted, that output in the y predictor. So we will compare y test and y predict in a data frame. I have written a simple code to get the prediction. See, actual is 46,000 and predicted is 45,900 something, so nearly. So it has made a very good prediction because this is a simple model, the data is not that complex. The predictions, so very close predictions, it has made a very close predictions. Even we can display in the plot. Let's see, I have plotted it, actual car purchase amount versus predicted car purchase. They are all on the same line, they are all on the same line. That means what does it means? What does it means? This is overfitting, data is like overfitting, there is no error, like it's not good because it is just for learning the linear regression model. I'm showing you this. So it has very good prediction, it has predicted approximately right. So this is not that good. Now let's check the metrics. Now we will check the model performance. To check the model performance, I have used like four performance metrics. One is mean absolute error, mean squared error, R2 square, and I will use adjusted R2 square. We import all this from the sklearn dot metrics. So mean absolute error. First thing is see. We are calculating, like basically the model performance is the error term, that is y minus y hat, actual minus predicted. So the error will be on the scale of purchase amount, that is what is our car purchase amount. If we see that, see 35,000, 45,000, 42,000. So it will be on this scale, it will be in the dollars, US dollars, or by how much is the error, like $100 error, $200 error. What is the actual minus predicted will be on the output variable scale. Okay, so that is very important, on what scale you are calculating the error. So I am so y, see here, y test minus y predict. So mean absolute error is the absolute difference between actual and predicted values. So if you see the y test and y predicted difference, it is less. Sum of absolute difference between y test and y predict, it is very less, $212. So that is very less error. So model is performing good. Model is performing good. Even you have seen here, even you have seen in the graph that it is giving very approximate values. So model accuracy is good. Mean squared error. Mean squared error is the average squared difference. That's all. Average squared difference. What is the, like, are you understanding? See, y minus y hat square. This is mean absolute error. This is mean squared error. Sorry. Y minus y hat is mean squared error. Here it is squared. If you are calculating absolute error, then we don't square it. It's just an absolute value of y minus y hat. So in the cost function you get this. So this is the mean squared error, and only this part is summation of y minus y hat is mean squared error, and y minus y hat absolute will be mean absolute error. Even the mean squared error is less, that is only 62,000. Because it is squared, the value is more. It looks like oh, very not 62, but if you are squaring it, it's less, it's very less if you are not squaring it. So mean absolute squared error is also less. So model performance is good. R2 square, I have told you the variation in the target variable. What is R2 square? See, I have told you R2 square, actual minus y minus y hat divided by summation of y minus average y average value, y bar. So R square value, if it is near to 1, it is as good accuracy. If it is far from 1, then it has low accuracy. In our model, R square value is 0.99, and it is almost 1. So in the real world, you should not get such a high accuracy. That means the model is overfitting or underfitting. There is some error. So this is not like good practice. This is just for understanding. So 0. We are getting a very high accuracy because our data is very clean and very simple data. So we are making very accurate predictions. So 0.99 is a very high accuracy, and it is not practicable. Our accuracy should be between 0.8 and less than 0.9. That is a good model. So R2 square is 0.99, and I also calculated the adjusted R2 square by using the formula C here. This is the same formula which I have mentioned here. By using this, we have calculated the adjusted R square, and see, very, because this model has very high accuracy, very minute difference in the adjusted R square and R square. There is a very little decrease. If you like use very complicated data, then there is a very good decrease in the adjusted R2 square. So by evaluating all the metrics, I have plotted I have made a data frame where the metrics and values given: absolute error, mean squared error, R2 square, and adjusted R2 square, and interpreted the evaluation results. That is what same which I have explained. You can go through this in my GitHub. You can download the notebook. You can open the notebook and read the interpretation very carefully. Next, this is for model assumption, residual plot. Residual, what is residual? Y minus y hat, actual minus predicted. So by calculating the residuals, I have plotted the residual plot. This is the residual plot. See, predicted car purchase amount and residuals, error. Residuals are error. So data is randomly scattered right here. So if it is randomly scattered, then the linear assumptions are satisfied. If it is not random, then homoscedasticity is met. This is known as homoscedasticity. If the error is randomly scattered. If it is not randomly scattered, if it is confined at any one point, or if it is accumulated at some other somewhere here or somewhere here, or if it is looking like fan shaped. Fan shaped is some like it is randomly scattered here and accumulated at the center and randomly scattered here. So if you get something unusual pattern in the residual plot, then the linear model assumptions are not satisfied. Then there is a heteroscedasticity of data. The homoscedasticity, this is homoscedasticity, that is residual is randomly scattered. That's what I have mentioned, is this is the linear assumption. So I have also shown you right here the best fit line. We have to find the best fit line in our data. So best to identify the best fit line, we use the convergence algorithm, find the gradient descent curve to find the global minima on which we will get the best fit line. So the best fit line here, if it is simple linear regression, only one input and one output variable, it is easy to show. But we have many five dependent independent features here and one output variable. So what I did is I have plotted a best fit line plot with only one single feature to show you the best fit line using the annual salary. Using the annual salary, I have plotted the best fit line. See, it somewhat looks like this. So the best fit line, linear regression, and our best fit line is like this. So this is how the model has built the best fit line by identifying the global minima. This is the by using only one independent variable, annual salary versus car purchase amount. So you can plot like for all the other variables, but that's not necessary. When we are doing the multiple linear regression, this is just for the demonstrating how the best fit line looks. So here the data is scattered and this is the best fit line. With this best fit line, our cost function will be less, that is our error will be minimum with this global minimum. That this is important. So this completes our linear regression theoretical and practical demonstration. I have added the GitHub link where you can download both the notebook data and the theoretical also. This is data car purchasing data.csv. It is in CSV format, and this is the notebook for learning the coding and understanding the practical implementation of linear regression. And this .pdf, this is the theoretical notes which I have explained you. This might help you. We can go through the brief summary, brief explanation as well. So thank you all.